Log on, tune in, find out. Another good idea from Cambridge.
Professor T.A. Slaman, Ted Slaman, from University of California, Berkeley. We speak on number theoretic consequences of Ramsey theoretic principles.
Okay, thanks. That's the first time I've ever been introduced as T.A. Slaman. Usually my friends just call me T.A. I want to talk about connections between recursion theory and, let's say, logic. And the motivating question is this: what number theoretic principles or what number theoretic consequences are there of infinite, familiar infinitary principles? And by number theory here, I just mean expressible in the first order language of arithmetic. So not particularly the sort of things that show up in number theory textbooks, but things that are stated in the language of first order arithmetic. Okay, so the motivating question is, when do arguments involving properties of infinite sets enable us to conclude facts about the finite sets? And I wrote this thing new means that it's going beyond what we've already assumed is true for the finite sets. Okay, so if we have a principle, for example, I'll get to in a minute, I'll point it out. Okay, so that's the question. Now, in order to phrase that question, I'm going to set it up twice. The first time is model theoretically or semantically, and then we'll look at it formally. Okay. So a model of second order arithmetic, this is a structure like Antonio was talking about, consists of two things. It consists of a version of the natural numbers and then a version of the power set of the natural numbers, which are supposed to be some representation of the infinite set. So there are the numbers of the model, and then there are the reals of the model. The kind of analysis we're trying to do is we're trying to look at effective arguments. Right? So wherein you have some algebraic properties or combinatorial properties of the infinite sets. You use those properties together with very explicit calculations, things that you can define relative to the reals that you're allowed to work with. Like, for example, you might have in hand a random real, and you want to see what you can use a source of random bits to how can you use a random real to tell you facts, number theoretic facts, right? Or you might have some kind of infinitary combinatorial principle, and you want to apply it directly to conclude something about finite combinatorics. Okay? And that the application being direct means you don't suddenly whip up all kinds of other real numbers and use them in your proof. You have to use only the principles that you have in hand and effective manipulations of the sets that those principles provide for you. Okay, so this is the sort of formalization of or an attempted formalization of what I just said. RCA naught stands for recursive comprehension axiom. The 0 stands for limited induction, effective induction. It's the algebraic part of piano arithmetic. Induction, I means induction. Sigma 1 means restricted to sigma 1 formulas. So existentially defined, existential formulas. Induction just says if you have a sigma 1 formula, if you have an RE set, V defines an RE set, 0 is in the set and it's closed under successor, then the set contains all the numbers. That's sigma 1 induction. Okay, and then lastly, recursive comprehension. The reals are closed under join and relative computation. So recursive is the same as delta 0, 1. And we want to know, given some second order principles, what first order principles, what principles about n up there can we conclude? And this is what we're allowed to use. This is a formalization of what we're allowed to use. Okay, a particular kind of structure of second order arithmetic is an omega model. An omega model has the property that the natural numbers of that model are isomorphic to the natural numbers. Okay. The reals of M form an actual collection of reals, and they're closed under recursive n, so it's an ideal in the Turing degrees. An omega model is a particular structure like that, where you have the natural numbers and some ideal in the Turing degrees. Now, I would love to, but I don't know any way to recursion theoretically address the question of what number theoretic facts can you prove from second order principles. In recursion theory, we work with the actual sets of natural numbers. We can't manipulate the theory of arithmetic if you already decide what the natural numbers are. Right? If you fix the natural numbers and you look at the different kinds of definable sets, you can't analyze arithmetic truth semantically because you've already fixed the model in which you're working. You don't have any way to talk about this number theoretic fact, right, couldn't have been proven, or it might have not have been true because you've only fixed one set of natural numbers. So I don't know a way to recursion theoretically get to the question that I want to get to. And so instead I have to go through this formal business where we have to look at non-standard models. If we're going to analyze things semantically, we're not going to get into the details of proof theory or proof theory relative to these systems. Right? We're not going to do a formal analysis, we're going to do a semantic analysis. Then we have to work with standard models, omega models, and possibly models that are non-standard, where what's true in the first order structure is different between the first model and the second. Okay, so if you want to show that some principle doesn't prove some statement, then you have to find a structure in which the principle is true and the statement's false. Okay, so if you only use the natural numbers, the actual natural numbers, you have very limited ability, right, because you fixed the theory. You've already fixed everything that's true. Okay, so you have to work with non-standard models. You have to work with these models of second order arithmetic where the first order part's non-standard. Okay, so expect that to come. Okay, so now what's a typical sort of theorem here? So I want to give an example. Suppose that you have a model of arithmetic which has p minus plus I sigma 1. So it has the underlying number theoretic principles we've assumed. Then there's a model M that can be obtained just by adding sets. You don't change arithmetic, you just add sets. You augment this model of first order arithmetic to a second order structure by adding sets. And you satisfy recursive comprehension. So which sets should you add? The recursive sets. Right? If I just take a model of p minus plus I sigma 1 and augment it with the collection of infinite sets that are computable in that model, then you get a model of RCA naught. Sigma 1 induction holds relative to any computable set if you have a model of sigma 1 induction. So that tells you a fact here. So this is an example, right? It's a simple example to see, or it's at least plausible if you haven't seen this kind of thing before. It gives you an example where RCA naught tells you the existence of a lot of sets. Right? There's a whole algebra of sets, and they're closed under recursive n, but it has no new first order consequences. Because any model of I sigma 1 can be extended to a model of RCA naught by adding sets. It doesn't change arithmetic truth if you add some new sets. Right? You haven't changed what the numbers meant, what it meant to be a natural number. Right? So any statement that's provable from RCA naught is provable from this first order theory. Because if a statement is consistent with this first order theory, take a model of it, augment it to get a model of RCA naught. Now you've got a model of RCA naught in which that sentence is also true. So the first order consequences of RCA naught are completely identified by p minus plus I sigma 1. Just the existence of infinite sets doesn't tell you new number theoretic facts. Okay? That's called a conservation theorem. You can have a second order theory, right? Doesn't prove any new first order statements. That's not the kind of situation that we're interested in. Right? We want to see when does the infinite apparatus give you more about finite sets. And Ramsey's theorem is such an example. So Ramsey's theorem is like a pigeonhole principle for finite exponents. You take a partition, for people, hopefully this talk's not going to do much for somebody who's never seen Ramsey's theorem before. But Ramsey's theorem, and we're going to be looking mostly at Ramsey's theorem for pairs. Ramsey's theorem says you take the natural numbers, you partition the size n subsets of the natural numbers into, say, 2 pieces or finitely many pieces. Then there's an infinite set such that all its size n subsets land in the same piece. If n were equal to 1, you take an infinite set, you partition it up into finitely many pieces, one of those pieces is infinite. Okay, so that's the pigeonhole principle. Ramsey's theorem is an extension of the pigeonhole principle. Now, what are the first and second order consequences of Ramsey's theorem? What does Ramsey's theorem entail about the integers? And what does Ramsey's theorem entail about the existence of sets of other type? So how can you use this kind of combinatorial principle to prove facts about finite sets, facts about infinite sets? Okay, and there's the recursion theoretic analysis of, so Ramsey's theorem has been studied quite a lot. It's a rich source of ingredients in combinatorics, logic, etc. The recursion theoretic part, there were two main phases until recently. Jacques in the 70s showed that for Ramsey's theorem for pairs, right, there is a computable partition of pairs such that it has no infinite homogeneous set which is recursive in 0 prime. So Ramsey's theorem is in particular not effectively true. It's not the case that given any recursive partition of pairs you can compute for it a homogeneous set. You can't even computably approximate. Secondly, there's a recursive partition of triples, so not only is every homogeneous set not computable, but in fact every homogeneous set has a lot of information. You can compute the Turing jump. Formally, that says Ramsey's theorem, so the first one, Ramsey's theorem is not effectively true. It says that RCA naught does not prove Ramsey's theorem for pairs because the natural numbers together with the recursive sets do not satisfy the statement of Ramsey's theorem for pairs. Right? There is a recursive partition, there's a partition there, and there's no homogeneous set for it among the recursive sets. Okay, so it's not the case for recursive sets that every partition has a homogeneous set. Okay, so that's this first thing. RCA naught does not prove Ramsey for pairs. Ramsey's theorem for triples proves that the reals are closed under the Turing jump. That's called arithmetic comprehension. Okay, so that's the first wave of facts. Second one is due to Seedapin in the 90s. And Seedapin showed that Ramsey's theorem for pairs does not prove Ramsey's theorem for triples. Right? Ramsey's theorem for pairs is consistent with no set compute 0 prime. Okay? There is an ideal in the Turing degrees such that the ideal is closed under the existence of homogeneous sets. Right? For every partition described in the ideal, there's a homogeneous set in the ideal, and yet the halting problem is not computable and is not an element of that ideal. Okay, so Ramsey's theorem for pairs is consistent with not arithmetic comprehension, because you can have a structure in which there is a delta 0-2 definition and no set satisfies that definition, right? Because 0 prime is not in the ideal, but every partition of pairs has a homogeneous set in the ideal. So the ideal is closed under Ramsey's theorem for pairs. It's not closed under the Turing jump. And this is a typical way that recursion theorists show that one second-order principle does not imply another. Again, an ideal in the Turing degrees, it's closed in one sense, not closed in the other sense. Okay, and there was a long-standing problem which was posed by Seedapin originally, which was, is it the case that Ramsey's theorem for pairs proves that the Cantor set is compact? And so compactness is another infinitary principle that shows up often in mathematical, shows up all the time. Right? And so in Seedapin's proof, and in fact all the others up until recently, of ways to build an ideal that's closed under Ramsey's theorem for pairs, there was an embedded application of iterated compactness. And so Seedapin raised the question, is compactness a consequence of Ramsey's theorem for pairs? And the weak Kernig's lemma is the assertion of compactness of the Cantor set. It says every binary infinite tree has an infinite path. Okay, so then recently, this is one of these, if you don't know the story behind this, if you haven't heard about this guy, this problem was open since the mid-90s and received a fair amount of attention. This kid, an undergraduate at a very small, modest university in China, solved it. It's one of these out of the, somewhere out of the unknown genius comes up and gave a really brilliant solution to the problem. And he showed that, in fact, Ramsey's theorem for pairs does not prove that the Cantor set's compact. One of those greats, like we should make a TV show about that or something. It's one of these. In fact, there is one in China, I think. So, and he's also applying to graduate school now. So it's unbelievable, and having trouble getting in because his grades aren't that good. No, I'm not kidding. That's really true. So, okay. But in any event, this name may come up again in the future in recursion theoretic meetings. I hope so. Anyway, so a really interesting side story. Okay, now, Ramsey's theorem for pairs. So Ramsey's theorem for pairs, we know how it compares to compactness, right? We want to understand it, and we also want to understand what does its number theoretic content. So Ramsey's theorem for pairs has a second order analysis. So it can be decomposed into what seem to be in a nice way. Right? First, the decomposition is what's called stable Ramsey for pairs and the cohesiveness property. So Ramsey's theorem for pairs is equivalent to a conjunction, a weaker form of Ramsey's theorem for pairs and something called cohesiveness. So let me say what those are. An infinite set is cohesive. I have some array of sets, R0, R1, etc. Okay? X is cohesive for that array if for each element of the array, X is eventually contained in or eventually disjoint from that element of the array. So X as a set is measuring every one of those R's as either large because it contains almost all of X, or small because it avoids almost all of X. Okay, so X, the principal filter defined by X, is measuring all of those sets. That's what cohesive means. So cohesive, the word cohesive means you can't break it. It sticks together. You can't break it into two. So X does not break any of those sets into two infinite pieces. Okay? They don't break X into two infinite pieces easily. Okay, so that's the cohesion principle says that every family of sets has a cohesive set. And it's easy enough to put together a cohesive set if you try to build it. There's an induction, and I look at R0. Is it infinite? If so, then I'm going to take all my numbers from R0 and now pick a number and put it in. Then I look at R1, intersect it with R0. Is that empty, or is it finite or infinite? If it's infinite, all my numbers are going to come from the intersection. Take a number, put it in, and so on. You choose what you've done so far could make your decision for you, right? Or you just choose arbitrarily. That's not recursive. That's not effective because the questions we're asking at each step is some set infinite? So you can't. The cohesiveness statement is not provable in RCA line. Easy enough to show. Okay, a partition, it sets this part. A partition is stable if for every X, the partition eventually settles on where the pairs that start with X lie. So if I think of the partition as a coloring of edges, all but finally many of the edges that come out of X have the same color. Okay, so that's a stable partition. Now, the question that this is, so that was also done in the whatever it was in this when 10 years or so ago, this stable thing. Oh wait, where am I? Oh, I'm going the wrong way. Here. Yeah, so this split is about 10 years old, understanding stable and co. And then the question was, from then, that is the stable Ramsey theorem equivalent to Ramsey's theorem? It looks like it shouldn't be. Right? It looks like stability is a much stronger condition on the partition than what might be satisfied by an arbitrary partition. And so there's a couple of observations. If F is stable, then every X has an eventual color given by this limit as y goes to infinity f of x, y. And things that can be approximated right, in the limit are recursive in the Turing jump. So if F is stable, the eventual color of X can be computed from the jump of the partition. Now, if you have a set that's infinite and it's monochromatic with respect to eventual color, so it's an infinite set of all things that have the same eventual color, you can, from that set, compute a homogeneous set. I just take an element of my set, it's let's say, almost everybody is colored 0 with X. Then I look at my set till I find somebody, oh, this is colored 0 with X. Okay, now I'm going to take him, this pair. Almost everybody's colored 0 with X. Almost everybody's colored 0 with this thing, too. Find somebody that's 0 with both of them and put that in a homogeneous set. So it's finding a homogeneous set is equivalent to finding an infinite monochromatic with respect to eventual color set. And the jump can compute such a thing. Okay, so stable partitions, right, have homogeneous sets that are recursive in their jumps, unlike what Jacques showed about arbitrary partitions. Okay, so, and if you, it's a delta 2 property to tell what the eventual color is. So if you want to find a homogeneous set, you just have to take the delta 0, 2a, the things that are eventually 0, its complement is the things that are eventually 1. All I have to do is find an infinite set of one of those two, and I can get a homogeneous set. So stable Ramsey is equivalent to this recursion theoretic statement. Every delta 0, 2 property A, there is an infinite set H contained in her disjoint from A. How much time have I got? We started a bit late while I was setting this up.
Say 10 minutes more, maybe?
Good. Okay, thanks. Okay, so there was an initial attempt to separate stable Ramsey from Ramsey. I still haven't gotten to the first order consequences, but I'm coming to that. There was an initial attempt to separate stability from general partitions, and that was show that every delta 0, 2 subset of A, for every delta 0, 2 subset A of the natural numbers, there's a low infinite set which is contained in or disjoint from A. So there's a delta 0, 2 set which has the additional property that delta 2 in it is still delta 2. That's what low is. Okay, if that were true, then you could just keep adding homogeneous sets. You could build an ideal by adding homogeneous sets and preserving what is delta 2 in them, and never add a homogeneous set for Jacques's partition because you'd only use delta 2 sets. Okay, so that was a nice approach. That proposal was refuted by a theorem of Downey, Hirschfeld, Length, and Solomon. You can't do it. There's a delta 0, 2 set that has no infinite low subset in either it or its complement. Okay. So the recursion theoretic attempt to sort of control the complexity of the homogeneous sets that you add to make stable Ramsey true, right, is thwarted. Well, if you can't do the second order problem, you look at the first order problem. And so the first order part of the theory of Ramsey's theorem for pairs is bracketed by two results. The first is you can prove something new from Ramsey's theorem for pairs. You can prove this principle B sigma 2, which says basically if you have a finite set and you have a sigma 2 function on that set, you can bound the range by something finite. Formally, it says if a sigma 2 property holds of every element of a finite set, then there's a bound on the witnesses that you need to see that the property is true. Okay. So Hirsch showed that Ramsey's theorem for pairs proves B sigma 2. B sigma 2 is not provable in I sigma 1, so it's an anti-conservation theorem. Unlike RCA naught itself, Ramsey's theorem for pairs gives you new number theoretic consequences. Okay. It doesn't give you too much, though. Cholak, Jacques, and I showed that anything you could prove from Ramsey's theorem for pairs and I sigma 1, you could prove using I sigma 2, and no mention of Ramsey's theorem for pairs whatsoever. Okay, so you can eliminate the combinatorics, right? You can capture the first order part in this slightly bigger theory. Okay. But the exact identification of what you can prove number theoretically using a Ramsey, an appeal to Ramsey style combinatorics is open. So what is the theory exactly? Okay, in particular, is it as big as possible? Does stable Ramsey or Ramsey prove I sigma 2? Okay, so here's what I know now. Right? So the recent theorem of Chong and Yang proved that there is a non-standard model of our CA knot with the following properties. It satisfies stable Ramsey. It satisfies not I sigma 2, so stable Ramsey does not prove I sigma 2. Right? And it doesn't satisfy the conclusion of the result that holds in standard models. Right? It dodges the recursion theoretic obstruction by changing the underlying number theory so that the underlying model of arithmetic doesn't, you can't run the Downey, Lemp, Hirschfeld, Solomon proof. Right? That proof methodology does not apply in this model. Okay, so you change the underlying number theory and it changes the way definability in arithmetic goes in such a way that you can support an oddball model of stable Ramsey. Okay. So now it doesn't prove, everything here is low. Jakish's proof that there is a partition that has no delta 02 homogeneous set goes through in this model. Okay. So this model doesn't satisfy Ramsey's theorem. So it shows that stable Ramsey is somewhat weak. On the other hand, it has an interesting feature, which is that it relies on we have to customize this model. We have to build a sort of unusual first order part of this model and then add a lot of homogeneous sets for, close under adding homogeneous sets for stable partitions. So there's an unusual structure of arithmetic in this model. The way that proof goes is you need to know that within this model, every recursively propagated finitely branching tree of finite height is finite. So let me show you what, that's a lot of undefined words. Let me show you what I mean by such a tree. So recursively propagated, a tree is recursively propagated if I can enumerate it in this way. First enumerate the root of the tree. This is going to be recursively enumerated, not recursive. Then later, we may, if we wish, enumerate successors of some node that we've enumerated so far. Okay? At the moment, that's the only node we've enumerated so far. So later, we might enumerate finitely many successors, and that will be all the successors, all the immediate successors of this node. Later, again, we may enumerate some successors of one of these nodes. And then they don't have to come up by level. They just get enumerated like that. That's recursively propagated. You're growing it by a recursive enumeration. Okay? When you enumerate the successors of this node, that's all of them. You can't enumerate any more successors of a node that has successors. Okay? So it doesn't have arbitrary. When you enumerate the successors, you know the fan out of that node perfectly. That's recursively propagated. Now, if you have a recursively propagated tree and it has finite height, bounded by some b, the enumeration has to be finite. Right? You have a finitely branching tree of finite height, it's finite. How hard is it to prove that? Well, I'm going to prove that at some point I've enumerated everybody at level 0. Okay? That happened in the beginning. There's going to be a point at which the previous level has been completely enumerated, and then there's only finitely many nodes, and I will enumerate. I have a nice sigma 1 subset of a finite set. Okay? That enumeration has to stop. I can't take forever. This is that's sigma 1 induction. Can't take forever to enumerate a bounded set. Sigma 1 induction. But the induction hypothesis is take a step at which there are no more things being enumerated here, and then prove it that there will be a stage at which there are no more things enumerated there. This is a sigma 2 induction. So this principle of star is provable in sigma 2 induction. Of course, we're only working with sigma 1 induction. Okay? The theorem is that star and b sigma 2 are independent over I sigma 1. So this star thing is a different way to go in number theoretic consequence, right, than sigma 2 bounding. Right? It's something off to the side. It's a different property of the numbers than the property that we already know Ramsey's theorem proves. Okay? So then here's the question. This star thing showed up in a critical way in the in the model that we built, which could support Ramsey's theorem for pairs. Right? So we don't know, does stable Ramsey or Ramsey, even the stronger thing, imply star? I don't know. Right? If the answer is yes, then we're in a really interesting situation where stable Ramsey is a second order principle that characterizes some fragment of arithmetic, but it's not one of the standard ones that we know, which is bounding or induction. Right? It's, in most of these situations, it's the Kirby-Paris hierarchy in arithmetic that measures number theoretic content. Right? And if stable Ramsey proves star, then it's a strict, stable Ramsey does not prove I sigma 2. And if it proves star, it's more than B sigma 2, so what the heck is it? I don't know. Okay, so there's some interesting things, but if you wanted to show that Ramsey's theorem or stable Ramsey is stronger than B sigma 2, the only candidate was show that it proved I sigma 2. That was the only thing that people could aim for. Okay, so now we have something else to aim for. Something that hasn't been hammered on for 10 years, right, with no success. Okay, so that's the first kind of question. The second question has to do, there's really two questions that I'd like to ask. The first one is, does the theorem, Ramsey's theorem for pairs with stable Ramsey theorem for pairs does not prove Ramsey's theorem for pairs, settle the issue of whether there is an effective proof of Ramsey's theorem for pairs from the stable Ramsey theorem for pairs. So we have a proof that there's no formal implication. Does that settle the issue of whether there's an effective way to go from stable to full Ramsey theorem for pairs? To me, it does not. I think it could well be that we could still use Ramsey's theorem for pairs and induction and prove, stable Ramsey and prove Ramsey by some iterated number of applications. But the proof's going to be like the Downey, Lemp, Hirschfeld, Solomon proof. It's going to use more induction. So I think that the problem is open. It doesn't settle the issue. That's my personal opinion. But by saying that, I'm also saying I don't think that this reverse math approach, the formal approach that the manifesto of the subsystems of second order arithmetic is that it is the foundation of ordinary mathematics and second order arithmetic. And the implication has been settled, but I don't think that the issue has been settled. So I don't accept the manifesto that second order arithmetic is a complete foundation for the subject. So I believe really the real question has to do with the actual real numbers, and that's the recursion theorist's realm, not the formalist's realm. That's my opinion about that. But we could debate that if you want. Okay, and then that leads to the actual, what I think is the actual question. Right? For omega models, does stable Ramsey's theorem for pairs prove Ramsey's theorem for pairs? And if so, what did you need to know about the numbers to support that implication? What did you need to know about the numbers to see that this implication is true? Right, so it goes both ways. Right? So you want to know what are the number theoretic consequences of certain second order principles. So you can see what you can prove from them, and you can build weird models in which the second order principle holds, but the number theory is weird. Right? You can also look at these kinds of questions the other way. The infinite sets behave in a certain way. Right? What is the necessary underlying structure of arithmetic, right, that supports that behavior? What is that behavior living on? Right? That's, it's just the contrapositive, right? But if you think of it that way, then you're led to a different class of questions than if you think of it in the first way. Okay, thanks.
Can you say a few words about the model you constructed and the construction?
This
Is
one.
it just, yeah.
Yeah, so the model that you construct, the model that you construct has two properties. The first is that, here it is. We'll call it N. Okay. You build this structure up by a sequence of end extensions of models of PA. Okay, so you have some model PA N1, you have a second model N2, N3, and these should all be sigma 1 elementary end extensions. So in other words, existential statements true in this model about parameters down here reflected down there. That's the first part. Secondly, it has to have you have to build in a failure of sigma 2 induction. And you build it in the most elementary way. You have a sigma 2 statement such that it's not inside here, there are no solutions to that sigma 2 statement. Right? You have a sigma 2 definable set. Inside here, it's empty. But here, in this model, it has exactly one element. And in this model, it has another element, and so on. Okay, so you have a sigma 2, something that's happening in a sigma 2 way, which happens once, twice, 3 times, once in each model. And you have to engineer it. You need the right kind of sigma 2 predicate, which is like a Gödel-Rosser sentence. Because you know how to make a new sigma 1 statement true, you add not con PA. Right? You can do the same thing here to make a sigma 2 statement true, you add not con PA plus the universal theory of arithmetic. You know, the true pi 0, 1 theory. So you have to customize it. So you get a new sigma, you get a nice sigma 2 definable omega sequence in the model. So this model it doesn't satisfy I sigma 2 because omega is sigma 2. Right? And, but it has a lot of nice reflection that sigma 1 statements, you can't tell between the whole model and every initial segment. And the initial segments are highly closed. They all satisfy PA. And then the last thing that you need is that the model is saturated, in that every definable subset of omega in this model has a non-standard end extension to a finite set in the model. Okay, so it's easy enough to, given a set X, build a model so that X is an initial segment of a finite set of a non-standard set. It's Gödel's theorem again, right? Or consistency. It's a compactness theorem. Given any set X, I can find a model PA such that there is a finite set whose first digits agree with X. Okay, so you need to do that for this kind of model, for every X that's definable in this model. That's the model. Okay. Now this model has, if I had an enumeration like this, one thing goes in, 2 things go in, et cetera, this enumeration would reflect to these models of PA. But since the models of PA are so closed, right, the proof that this thing being enumerated is finite would live inside this model PA, and hence it would be finite. Okay, so you can sort of see that this model naturally satisfies that principal star. That's the model. Okay. And okay. Obviously non-standard. Okay.
That was answered already.
Oh, okay.
All right. Well, okay. Thank you very much.
Thanks.